Welcome back. So in the previous lecture, we've just looked at how to initially represent planning problems, but now we're going to get into the meat of it, which is the search process, okay? So we're going to need some way to translate our original problems into an abstract space where we're going to actually conduct search, solve the problems. What this means is essentially we are looking for, essentially search is maps. It's looking for a mapping, a translation, and what it is doing is it's matching states, mapping states from the state space, to what we're going to be calling nodes. So these are search nodes in a search tree, okay? So that's what we're looking for. That is really what we're going to be doing in search. We need some way of taking the initial state. I am at location 2, 3. What does that look like for search? When I move from this state, what does that look like for our algorithms? How are we going to be able to interact with these? So I'll have a quick look at this. Essentially what we're going to be describing is a tree, a search tree. It begins at what we call the root, okay? So we have some form of root node. What is maybe less intuitive when you first see this, but we often forget immediately. Unlike a regular tree growing upwards, the tree is going to grow from the root downwards as we look at all of the possible options we can do at every location, at every node, right? So we're going to have essentially what starts to look like a tree, right? You have these branching decisions that go outwards. They don't always have to be 2, right? Sometimes you can do more at certain locations than you can at others. We have a growing tree that spreads out. These connection points we're going to be calling branches, right? Makes sense thematically. And so the final nodes here we see at the end of the tree, similar to a tree, right? The branches end in leaves, okay? So these are the leaves of the tree. It starts at the root, it branches outwards. At the very ends we have leaves. This is also often called either the frontier, right? It's the number of things that we've reached in our search tree as we grow outwards. These are the things that we've found. It can also commonly be called, as you will have heard when we actually get to the algorithms themselves, this will be called the open list, okay? So that might mean nothing to you right now, but we'll be getting there very soon and it'll all make sense. And then in terms of terminology about how we're going to interact with the tree, we start with a root node, and what we do when we generate new children is what we call expanding a node. So in order to expand our current node, any node n, this is where we look at the possible actions you can take from the corresponding state, and then we generate a number of children. In the other example, I've just been doing a binary tree. There's only the 2 options, but there can be any number of options, right? So what you're doing is you're expanding, you're saying what possible children can I generate, can I reach from this node? So expanding is really important. We often call this, the length of the things you can do, the branching factor B, okay? Again, coming from the nomenclature that makes sense. Right, so once you expand a node, you're looking for things to generate. Generate, I've been using this term, so what does that actually mean? In this way, right, we had our initial node, we've looked at the things we can do. We are going to look at each of these nodes individually, and then if it is a valid state, a valid location or otherwise that we can actually reach, this is when we decide to generate it and we're going to place it into the tree. So for example, here, this child here that is missing from the tree was not generated, which suggests that perhaps it was a blocked area or things like this, right? It was not valid to generate. We did not generate it. We did not add it to the tree. We did not add it to the frontier, the open list. Okay, so the branching factor is essentially the number of actions we can do in the tree. If we look at our example over here, this here, the branching factor B equals branching factor. In this case, it's just 2, right? We kind of see that all the nodes, the maximum number of nodes that it can generate is 2. So this is always related to the actual problem you're solving. Say you're in a grid world and you can move in 4 directions, your branching factor is probably going to be 4. So this is inherent in the problem we're trying to solve, and it comes from there. Binary trees are just a very, very classical situation that we use very often just to describe and to show these things. They're really easy to draw and to talk about. So the other aspect of this, though, is we have both the branching factor, which is essentially the horizontal size of the tree, but then we also have the idea of how far down we have traversed the tree, or what is essentially the height, the vertical height of the tree. So we call this term the depth, d. d equals depth. So in this example, the branching factor here is 2, right? There's 2 decisions, whereas the depth is how many times we can go down, so 1, 2, 3. Here we have a depth of 3 in the tree. So as part of this discussion on the search tree, here I've drawn a search tree of arbitrary size, right? So we have a depth of 3, a branching factor of 2, but why did I stop? So let's talk about the original problem, what we're actually trying to solve, right? So the root node here in a search tree corresponds to our initial state. Where did we begin in the environment? What we're missing and what we haven't talked about then, of course, is the goal state. Where are we actually trying to go? What are we trying to do? What are we trying to solve? So what actually is going to happen is that the search tree is just going to continually expand nodes, generate nodes, grow in size until there are 2 possible outcomes. So outcome 1 is that we're actually happy and we find the goal. So what that means is one of our leaf nodes will correspond to a goal node. We'll reach it, we'll discover the goal, and then we can end and terminate the search algorithm. We're happy. However, in case 2, what happens is that we will have exhausted all nodes in the frontier. So at this point in time, we can actually conclude that there was no goal node we could have reached. There was no valid solution at all in the original problem. That can happen. So what that means then is that the overall size of this tree, the size of the nodes that we could generate, that is what we call the search space. Note that the search space and the state space, while related, can be wildly different sizes and represent different things because of this mapping to an abstract space. Sometimes a search node could overlap with states easier, or we can, as we talk about both exponential and polynomial domains, the search space can grow rapidly, unlike the finite state space. So we'll get to that soon. So this is essentially the foundations of what the search process is. We're going to be constantly talking and interacting with search trees, which I think is both a really nice intuitive concept, and it makes it really easy to visually understand and to follow and to trace the behavior of our algorithms. And so then this leads us into what we'll be talking about next, when we actually start looking at what nodes are in the tree, right? So in part of this discussion, we haven't actually honed in on what are these magical circles? What are they storing? What are we actually using these for? Why were these useful as an abstract representation of the initial states? So please join me in the next video as we dive into that. See you there.